Our glazing systems have got to be able to accommodate that type of vertical building structural movement. Later on, Javier is going to get into lateral building structural movement and some of the issues associated with that and limitations of manufactured systems. So this kind of is one of the areas where we can see that in this slab, somebody has done a good job of showing that at the edge, there is that deformation. And so if we have sticks in there for that, I think this was a Connier reference. So you can see out in the middle, it might be deflecting. If this is 30 foot, this out in the middle, it may be deflecting up to an inch. That's what structural engineers of record that are designing buildings are allowed to design, and it's called L360. Unfortunately, a lot of the glazing systems are not really designed to be able to accommodate those types of movements. The structural engineer of record, which that's my background. I came from Burns McDonnell, one of the major players in structural engineering around the world and in the US, and I spent 7 years designing building structures. I was clueless about any of the requirements from manufactured glazed systems and what they require in terms of accommodating that building structural movement. Had no clue about it. So I'm letting you know, building structural engineers around the US, we've been in this battle. We engage in it to try to educate the community, architects and structural engineers and glazing contractors about the limitations of glazing systems to accommodate that. Every once in a while, we'll see something like this out of the structural drawings, and it gives L/360 or a half an inch of building structural movement. This is good. This is actually a good structural engineer that says, okay, I'm going to spell it out for any of the glazed systems, the curtain wall, the storefront. It's a half an inch. This is abnormal. You don't regularly find this in the structural drawings. And so this is out of the ordinary, but it'd be great if they all did this because then it would make our life easier. So if we have a vertical structural movement of that beam where everybody runs over and it moves down, we have dead load anchors at every single floor. That means that this whole section of curtain wall that is supported by that dead load anchor, that all has to move down 1 inch. If it's a 30-foot beam, the structural engineer of record may have designed for L/360 for that 30-foot span. It may be 1 inch. So we might be able to accommodate it in that expansion splice, but what is the actual limitation associated with the glazing pocket? That's a big key. So for a stick-built system, does anybody have an idea of what that limitation might be for a standard off-the-shelf stick-built system in terms of structural movement accommodation? Half inch, 3/4, good guesses. It's actually a 1/4 of an inch. This is the standard of every single stick-built manufactured system that is out there. They don't spell it out on the websites. It's not spelled out very much at all. It's something that you really have to dig for in information in small print to find out what the limitation is. And so let me tell you right off the bat that if you have a dead load anchor at every single floor and you're counting on this to be able to accommodate 1 inch of movement, that's not happening. It can't happen. This is the big misunderstanding of structural engineers of record, architects, even glazing contractors, and a lot of manufacturers. It's not matching up. And we're trying to help in the industry get this information out there and make it available to project managers like yourself so that it doesn't get in the way in the future of the project. For unitized, it's much different because at each floor, there's an area where we can accommodate, and that's much more movement that it can accommodate, 3/4 of an inch up to a 1.5 inch of vertical structural movement. In addition to that, it's much better for in and out of the page lateral structural movement that Javier is going to talk about. But if we're not dealing with unitized, then we're stuck with what the manufacturer has in terms of being able to accommodate, and that's a 1/4 of an inch. All their details, even their head details, where you see a half an inch joint, it can only compress that joint to 1/4 of an inch. So all those standard details that you get off of their websites are built for 1/4 of an inch maximum structural building movement. This is a quote from a manufacturer. It has in small print, live load deflection, 1/4 inch maximum allowable. This is off their shop drawings. One of the manufacturers has shop drawings in the notes down in the small print. It's not to exceed 1/4 of an inch. It's out there. All of them are prevalent, 1/4 of an inch max. So what are the solutions that we can offer from an engineering standpoint to be able to accommodate building structural movement with a stick-built system? We can stack the system. In other words, these joints that we have in there, the splice joints, become butt splice joints. They carry load vertically down through and all the way to the bottom or an anchored floor. And we can do this for probably about 3 to 4 stories before it becomes too much of a load to be able to handle. All this, though, needs to be coordinated with the building structural engineer of record because they need to plan on what those loads are where we're stacking it. So it might be the 4th floor that we stack on and we load. They need to know what those loads are if we're going to stack that up. What it also means is up at the top, it can actually expand all of that distance up into whatever we have available to be able to make that movement happen. And so we need to really plan for that joint up there because it's going to gain a lot of expansion and a lot from building structural movement. If it's a roof, that roof is going to move up and down, for those roof beams as well. One of the additional solutions that we found along the way is some manufacturers out there of stick-built systems are starting to understand the problem. And so they're coming up with hybrid types of joints to be able to use every 3rd or 4th story and be able to accommodate that building structural movement in a flexure type of a joint, a neoprene type of a seal. But this is really unusual, and you have to dig for those types of details if you have a problem like that. So for unitized, it's very easy. Like I said, you can dead load at every floor, and it can accommodate that type of movement. What about at the head? So over here, we have cold formed steel, and we have a steel beam that's up above this, and it's supporting this off of the cold formed steel. It's not a header, and it stretches for a very long way around the perimeter of the curtain wall. And so this is a movement joint. Like I said, all the standard details are a 1/2 inch. You can only compress a caulk joint up to 50% before it bursts and it is no longer a good seal. So it's 1/4 of an inch there, unless you do something special and design an extra large caulk joint or some type of other joint to accommodate that. So for caulk joints, Dow actually has a formula for being able to calculate the actual width and the thickness for that type of building structural movement. And ultimately it works out to be, about 2 times the movement. So in other words, on a 30-foot beam, we have that 1 inch of deflection because the structural engineer of record didn't know the limitations of a glazing system. And 1 inch is the amount that this joint wants to move down. You would have to design a caulk joint of 2 inches to be able to accommodate that in compression so that it only compresses 50% of it. The architect isn't going to accept that. And that's part of the issue that we have to be able to kind of get into early on a project to be able to show, hey, there's got to be some different solutions worked out for building structural movement. It's the number one misunderstood area associated with glazing systems and manufactured glazing systems. Every once in a while, we'll see something, from Conair or Oldcastle that looks like this for a head joint that has large building structural movement that needs to be accommodated. But this is, again, an unusual detail. You really have to dig for these types of details. Another one is EM seal. That can be used. Very expensive, though, to be able to use EM seal in those large movement types of joints. So what about storefront? What are the limitations associated with storefront systems that are just standard off the shelf storefront? This is a 21'4" long area of storefront, standard storefront. Does it require a movement joint at the head? And also, it looks like this where it's got hard shims at the top of it. Does it accommodate building structural movement? Does it accommodate this steel and the cold form steel coming down on top of that? No. The architects always show this detail with just standard tight shimmed conditions without understanding that it's got to accommodate building structural movement 95% of the time. And so we do have some rules of thumb that we have developed. So this is the instance of cold form steel framing. You can kind of see that there's a header that spans across. The maximum span for cold form steel headers is about 15 to 18 foot. So anytime that you have storefront that's longer than that, and it's underneath cold form steel or in the middle of cold form steel, it has to be supported off of a beam that's above that moves, and that requires a receptor head for your storefront. This is one of the conditions that we see very often where we have storefront that comes in up underneath a beam that supports some frame out. And so this does require some type of movement. Unfortunately, it's not shown right. It's shown, solid by the architect. And so that's in error. It does require a receptor head at that location. A receptor from a manufacturer typically range in capability of being able to handle that building structural movement, usually about plus or minus 3/8 of an inch. That's the maximum amount that receptor can handle. So again, whenever we enter into a situation where a structural engineer of record has designed a 30-foot long beam for L over 360 and we have 1 inch of movement, will a receptor accommodate that? It's not going to accommodate, 1 inch of downward movement. And so something needs to happen up front, early on in the project to be able to get some attention to that issue. Otherwise, we can have some major leaks. If there is that actual movement where people come over to the edge and are all looking out, it will be an immediate item to where something will break, a seal will break, but then people go away. The live load goes away. The seal is broke and people are running around thinking, why is it leaking? We don't understand what's happened. The problem was it wasn't designed right. It wasn't designed for the building structural movement. Almost 90% of the time, that can be tracked back to an improper design. Some rules of thumb for storefront receptors. If it's a canopy that you have overhead over that storefront, most likely it needs a receptor because that canopy is going to receive a lot of loads and it's going to move it back and forth. If the opening is longer than 18 foot in horizontal area, its vertical movement is required. And so that's a definite need for a receptor head. If it has dedicated wind girts, in other words, if there is a beam that is just supported without supporting the floor, it's a wind girt. It does not need to have a receptor. Precast tilt-up walls, you don't have to worry about receptors in those types of buildings. And ultimately, an engineer really needs to be looking at this from a structural perspective of what did the structural engineer of record for that steel building or for the concrete building, what did they design for? If it's not spelled out in the structural notes, it really needs to be investigated. So with that, I'm going to go ahead and turn it over to Javier. He's going to talk to you about lateral structural movement.
Thank you, Stuart.
Sorry, I think I advanced.
There you go.
Yeah.
Can everybody hear me all right? Yes. So, storage risk. The West Coast is the highest seismic area in the United States, and we have a part of our delegated design review includes making sure that when there is drift during a seismic event, that our curtain wall can accommodate this drift without causing the glass to fail. The building code allows about 2% of drift from one story to the one above. It depends based on risk category and the type of construction that we're installing the curtain wall, but 2% is a very common number. So for a 12-story high interstory height, you would expect about a 2.8 inch of drift between one story and the one below. So what does that do to our glass? If you think about it, let's take this TV over here, for example. It's framed with horizontal mullions and vertical mullions that are running and capturing the glass. The aluminum frame that captures the square glass is quite a bit more flexible than the glass itself. The TV here will remain on a rectangular shape, while your aluminum will now take the form of a rhomboid like this. So our review needs to make sure that not come in contact with the aluminum frame when there's a seismic event. The reason behind that requirement is that if it does, we run the risk that the glass might shatter, break, and become a falling hazard to the people outside of a walking surface. The ASE 7, which is basically the Bible for loading in the US, has on chapter 13 has the equations and has the requirements for us to check this delta fallout requirement. There are locations where you could be exempt of that requirement. And again, making sure that this big piece of glass doesn't fall and break and fall into a walking surface is what the ASC 7 is trying to achieve. At JEI, we have put together a very comprehensive flow chart, and it might be daunting to see this, but it's a very comprehensive approach to how do we help our clients flag and tackle some of the high seismic area of location as glass is getting bigger and bigger in locations where you might have 3-4 inches of drift. Stories are getting also taller. This flowchart was shared with a group of other structural engineers and PEs here in California, and it was validated. Actually, we had the pleasure to talk with one of the committee members that sat on the committee for ASC 7, Chapter 13. Basically, he told us, yes, this is basically the best way forward to tackle. It is such a young industry, the glazing industry, that the seismic requirements are quite young. So it's upon the delegated design engineer to make a lot of judgment calls on these cases, but there is progress on the codes that it's becoming a more prescriptive approach. Allows us to take advantage of the testing that is done on a lot of the systems that are manufactured. And I'll show a video after this slide in which frame is tested laterally and racked dynamically. And if there's no glass that either breaks or falls off the frame, then the system is good. The problem is that many times on the project, the sizes of glass, the BLOs, are quite a bit larger than the tested frame, or the mullions might be slightly different. So if that is the case, we can't really extrapolate the results of the test. We have to find more creative ways to validate that glass. JEI has internal equations that reference the ASE code that we can prove out based on equations if the size of the glass has enough clearance around the perimeter to allow the frame to deflect without the potential of the glass coming in contact with the frame. If for whatever reason our glasses are too big and we can't get the glass to check out, we have yet another set of kind of creative approaches to engage other types of equations to prove it out. If all else fails, we have a template of an RFI that we can send to the structural engineer on record and ask them, how much drift is this part of the building really seeing? And there have been times that the response was like, no, yeah, we have allowed a 2-inch full drift on this locations. But there might be other times that this particular part of the building is quite more rigid and it's not going to drift as much. And that RFI basically gives us a thumbs up to proceed with those sizes of glass. A couple of exceptions that I have seen that to prove out a very piece of glass is if the glass is installed 10 foot or below a walking surface, we don't need to worry about it. Because imagine if this big piece of glass breaks during a seismic event and it falls from the frame, it's not really going to hurt anybody walking. But if you have this piece of glass 3 stories up right outside the sidewalk, the last thing you want is people rushing out of the building in the event of a seismic and then have glass just raining on them. We really don't want that. And another solution would be to use a laminate outboard or an inboard. That way, if the glass comes in contact with the frame and ends up fracturing, the laminate captures the glass pieces in the frame so you don't have that falling debris hazard. This is the ALMA 501.4 testing that a lot of the big manufacturers have testing their systems, and I'll play this.
0.6.
That's 0.6. Oh, no. 0.4 is a static. Yeah, 0.6 is a dynamic. Yeah.
Might have to.
Oh, do it from there. Oh,
There you go.
Unitized systems have a lot of advantages for this type of movement, and I'll share that slide here in a little bit. But here's a video of that test. So you could see that the bottom, the testing apparatus basically has one part of the frame static while it racks the other one. And because if the whole building moves equally, then there's no differential displacement. It is a differential displacement, the one that really causes problems with the glass. And I do want to add that the SSG systems, the ones that are not captured, like the one in the test, there are very limited equations and analytical approaches that we can take to validate those systems. Most all SSG curtain walls have to be tested for us to validate it. And that's something that whenever we see an SSG curtain wall in a highly seismic area, that's one of the first things that we help our clients with, which is requesting test reports for those SSGs, because without them, there's really not a whole much we can do on the analytical front. Like a 4-sided SSG, correct. Yeah, there are, if it's captured at the head and the sill, you still have, on some mullions on the verticals do have a little tongue, and on the bottom, actually, they have the little chairs that hold the glass. But what's preventing the glass to come in contact with the other piece of glass is a silicone joint many, many times. So those would need to be tested as well. For a unitized system, like Stuart mentioned before, the drift of the unit above it, it's not gonna engage the unit below it. So it can slide with respect to the unit below. So this is one of the great advantages of unitized system in highly seismic areas, that each panel can deflect without engaging the one below. Thus, the big TV glass remains square and just rides along the piece of glass instead of being crushed by the rhomboid shape of the aluminum. A slightly different, you want to talk a little bit about the genesis of the fins?
Yeah, you've had a project, I guess, with some fins that have happened or occurred, and so
big spin involving that one.
Here's an issue that has occurred that I have seen, from my years of being involved in the glass and glazing industry. The manufacturers started out not envisioning anything that looks like a sail hanging off of a curtain wall. They didn't start that way. This concept was developed from architects wanting to be able to add certain shade into the building, and they did it without really consulting the manufacturers. And so ultimately, this is a big sale. Whenever you add these things on, each each mullion collects wind load from that sail, and it wants to move laterally. What that does is it bends this mullion in the weak axis along that axis where it's connected. And usually in the specs, it has a limit for the contract that it only deflects L over 360 of the clear span or an eighth of an inch. So if you have a 12-foot tall mullion, it can only deflect laterally 1/8 of an inch due to this wind load that's pushing on it, each one of them. And so this creates a nightmare of a concept, from the engineering standpoint, so that glass doesn't break. And so this needs to be communicated with the architects early. The earlier that we get involved in these types of projects, oh my gosh, we can help out. But if it's left to the tail end where the delegated design is, it's a crazy concept. They've left the design, the architects have left the design of the glazing systems all the way to the tail end, and it creates issues whenever there's things that are caught. So, and just get it in as early as possible.
And two things to add to what Sua was saying. If that gasket, basically the capture, the bite is lost due to that lateral movement, you can have water infiltration into the system. So that is one of the reasons that they want to limit that to only 1/8 of an inch, which is a very tight margin. Another item that is crucial, and this is something that we had to deal in that project recently, the amount of torsion that the mullion sees from that load, it's developed on the mullion, and we can reinforce the mullion with a lot of steel, and we can prove out that the mullion works. But now that load has to be transferred to the structure. If we have a concrete slab, I wouldn't worry too much about it. I mean, we might need to space our anchors a little bit more. But if the substrate is an 18 gauge or a 16 gauge stud, the light gauge metal is typically also delegated. It's also part of the delegated design. So the communication to the engineer that designed that gets a little bit more longer. We have to jump more hoops to get, but we need to let the engineer that designed the header of those studs, hey, now you're not only looking at a perpendicular load from wind, but there's also this huge torsion load that can induce very high.
So what he's meaning by that is this all wants to twist.
Yeah.
Like this. That's the
correct
torsion that
and the F&T anchors that are holding
anchors.
Yeah, the F&T anchors that are holding, that are sliding on top of it, are inducing a very high torsion load that might cause damage to the finished drywall inside, even failure of that header in locations. So that is something that we either want to put up in the drawings and the shop drawings, like big bold notes, reaction loads from wind are this, and from torsion are this, and make sure that the engineer that has designed that cold form steel is aware of this. And again, like Stuart was saying, bringing the delegated design team as early as possible can prevent so many headaches from this architectural additions to the curtain. With that, I'll send it back to Stuart.
Definitely something to be able to watch out for in the future as architects are becoming more and more creative with things that they want to do for shading, interior shading and energy. Another area, specialty area that you really need to watch for are short returns on curtain wall. In other words, if you have, curtain wall out here and it makes a short return, dead loads into the building, all of this from wind suction can actually deform this joint where it tries to connect into that building, and it's usually a sealant joint. And now it becomes a movement joint because it's trying to deflect these members outward and away. That needs to be looked at carefully because there can be a lot of movement in those types of joints. That's typically, if you go out to buildings and they're complaining of moisture problems, most of the time it's these short returns. You can actually go out and look at the sealant joint and say, oh, well, it looks broke. Yeah. And so a lot of stuff leaks in through those areas if it's not designed properly. Another one of the gotcha areas is most of the time, whenever we have curtain wall uh, mullions, they're very movement oriented. They're very flexible with the wind. And usually what we have adjacent to it is very, very stiff. It doesn't move at all in the wind. So this actually becomes a joint that needs to be designed for that differential movement as the curtain wall moves in and out of the frame of that stiff area over there. This has to be able to take that movement without breaking the seal. And so again, it's another number one area that we see as a deficit. A lot of engineers are not paying attention to this typical half-inch joint. If it needs to grow larger because we've got a very tall span of a curtain wall and it's moving back and forth, that's an early on thing that we can identify. In addition to that, corners need to really be looked at closely because in this case, a sharp corner, it actually receives wind load that is positive and wind load that is negative. It contributes to the bending, the weak axis bending of this mullion that's out there at the corner. And that is a real critical area that needs to be able to either be reinforced heavily to avoid that type of movement out there so it doesn't bust glass, or it needs to be able to be tied back into structure more often than the regular wind load clips. Be very careful of, some of the details where we want to run horizontals through. It's real easy to think about those types of things as solutions, but it might have an impact on the building structural engineer of record because in longer situations like this where we want to run a horizontal through, if we have cold form steel that has been designed by the structural engineer of record as a jam member over there, and we're trying to load into it, that can be a decent amount of load. And the structural engineer of record might look at it and say, oh, wait a minute, what are you guys doing? I didn't design for that. You're loading my cold form steel member now, and that's too much. So some of the framing layouts to avoid or to be careful with, whenever we have operable doors or larger openings, we definitely want to make sure that the structural drawings and the architectural drawings have some sort of a support system behind it. If we can get that early on, that can save a lot of headaches because there's a lot that we have to do to be able to carry large loads over this thin member here in a weak axis to be able to support the vertical loads and then the wind loads on top of that because we have other mullions that are dumping in wind load into that laterally. This becomes a very difficult horizontal mullion to be able to handle those types of loads, even with heavy reinforcing in it. So this needs to kind of be looked at early as well. Whenever we have differential movement in a building, it needs to be dealt with and sought out early. In other words, this is a cantilever area. This area down here, people are able to walk under it about 30 foot back. And so this on the cantilever, this moves up and down quite a bit as, people are running over to the edge of the glass or, loading it in a different way. This moves. But over here, where it joins the regular flat plane of the curtain wall, this does not move. This has to have two separate ways of being able to handle that movement whenever it goes from a cantilever to a straight flat plane. And usually that's done with a faux mullion. And so you just set a mullion that's an SSG back behind it. You have a joint that separates it. Usually the architect doesn't mind, but that needs to be discussed early on in the design concepts associated with the framing layout. Connections to avoid. So every once in a while, we see an improper connection that's proposed by detailers, and that would be connecting into the lower 1/3 of a structural beam. The reason why you don't want to do this is many times these beams that are on the outside of the building structure, many times they don't have a lateral support And what we can actually do is we can throw so much load into that beam. If it doesn't have that lateral support, it can twist the beam and potentially cause failure of that beam member. Something to look out for. You always want to load into where the structural engineer record shows it in the structural drawings up here, usually on the bent plate pour stop or up in the upper half of the steel. So we've covered a lot of different things about, some gotchas, the biggest one being building structural movement and some of the other stuff. What questions do you have for us? We'd love to be able to share with you, and kind of answer some questions. We were that boring.
I have a question.
So you're saying that the building codes for the city, they're resisting SSG type applications. They don't want to allow that at all. Is that due to the seismic concerns associated with it, even with testing? Not four-sided, but a cassette system. Okay. We have not really seen a lot of that yet, but is that even whenever the architect's design, is calling out for SSG and the architect doesn't even know? Yeah, yeah. It is a little bit more equations. I'm glad this concept the other. What we would be interested in, though, if you've got communication from the city associated with that, I'd love to see some communication about that, what they're citing, because that way we can actually, be very proactive in investigating that and being able to advise, clients.
We have recently been involved in a project up in San Francisco that had some SSG applications. So I'm wondering if it's more of a local LA. Yeah. That is interesting.
Yeah.
Anything with unitized? Have they flagged any unitized applications or it's fine? Yeah. Yeah. No, I'm not aware.
I've got a card over there. I'd love to see, he would love to see it too. And that way we can kind of look back at what they're trying to cite. Is it a
Yeah. No, I can follow up with, Nick, John, Michelle to get the conversation going. And like Stuart said, we would love to, if you get that notice of rejection or whatever, we would love to look at it and see like, why is it being cited? Is it a sustainability thing? Here in LA, they're big about, hey, making sure that you install something that's going to last longer than just like a few years. I don't know if the sealant may be something that they realize that the harsh environments of the heat here might dry out the sealant.
center of blast deflection is what they've cited?
Yeah. Yeah.
Yeah. What you're going above 20 miles, 20-story building, like got in the middle 10 miles per hour, right? That center of blast will deflect full to 3/4 of an inch.
Mm-hmm.
I mean, I've had some same for motion red.
Mm-hmm.
That's how they had to thicken blast too.
Yeah. But the capturing, I mean, the capture system basically does the same as an SSG. We do have checks that say, okay, along the edge of the SSG, there might be might be a little bit more flexible, but it's still four-sided supported. So, right. So
Yeah. No, that is a definite mystery. I'd love to be able to, like I said, see some information.
Yeah.
Yeah.
It was worse than it. Yeah. Yeah. Well, that was I'll look into this.
Yeah. We'll love that.
Yeah. Yeah. We can do some more
Appreciate
investigation on our end, find out what they're citing. Yeah. Yeah. Good.
Please.
Absolutely. One of our best ways of being able to serve clients is getting in early. And so we can actually do design assist. We can break apart a quote into some really early design assist as just a small amount and then have the rest of the engineering later on. Those types of projects flow along so easy and smoothly because we can look at the issues and the problems up front. So we love to do that with our partners. Yeah.
We've even offered a few times to share the building movement RFI template. So some of the project managers can send it as soon as they send their proposal even to the engineer of record, say, we need this yesterday because we need to know if we need head receptors. We need to know if we will need custom anchors, because even for curtain wall, you can't have a 3-inch head joint because your F&T anchors won't engage with the mullion. So now you're talking about having to do custom steel anchors with welds. So the sooner that the building movement is brought to the attention of the engineer on record, the better. And the savings are enormous in that sense.
Yeah, if you're looking for an RFI template to just start the conversation, say that you guys get awarded, we can send an RFI template over to you and it'll stay there just the same language. It basically spells out, hey, we need to know what the building structural movement is and blah, blah, blah. It, you know, if you're using L over 360, that's probably not a good thing, you know, but, and it can spell out that there's limitations, you know, for manufactured systems, usually about 1/2 inch. And we can kind of guide that process early on. You can have the template, send it out in advance without even us, you know, and you'll get answers back real quick. And so that's where we love to be able to be an advocate for our clients.
Yeah. And even a step before that, we would love to, it takes very little time for somebody with a level of experience of Stuart and the rest of the team to look at a set of architecturals or structurals and very quickly be like, yeah, you're probably going to need a head receptor there. Yeah. Or, oh no, it's all like precast concrete tilt up panels. You're good. It's just a punched opening. You don't need to worry about head receptors. So, and for those cases, you don't even need an RFI. We can give you a thumbs up saying we're quite confident that you can proceed without the RFI, the head receptors, and that whole discussion. So.
Changing load values. So I'm assuming that that is, you know, deflections after being too conservative. Yeah. So a lot of times in our process that we go through with the RFIs, usually they'll come back and they'll say, just, you know, it's this. and it's almost like it's a pat answer. And it will come back and say, okay, guys, you know, this doesn't work with manufactured glazing systems. Stick built, you know, we're really needing to have some actual calculated building structural movement. And that's whenever they'll come down. They'll outline it. They'll say, okay, over in this section, it's 1/4 inch. Over here, it's really about 3/4 inch. Over here, it's 1/2 inch, you know? And so they get more detailed about it. They will come down. So it's a process of working through that and trying to get the real answer. Yeah.
Now, if the question was regarding wind load, we do sometimes, some structural drawings do have the wind load pressures listed on the structural drawings. We do go through and compare those with what we have calculated in-house.
The heads of glazing systems.
Yes.
So let me back up to that area and I'll let Javier kind of talk. It'll be a similar type of.
And we're actually working on a project in San Diego now, in which it's a window wall system that is captured above and also on the jambs. So if you think about that, you have the floor where the window wall is resting will move laterally. The floor above would move some more, but the frame remains vertical. It remains rectangular. It just like rides along with the system. So in those cases, we don't need to worry about the delta fallout because again, you don't have a rhomboid trying to fit into a square rectangular glass. So in those cases, the drift joints would allow us to basically exclude that requirement and just call it good. There's no differential. Yeah. Basically what it all boils down to fitting a rectangular piece into a rhomboid piece. That's the premise of the whole delta fallout thing. And may I add, the delta fallout is a very dramatic name that ASCE 7 chose, but it's because it's not that the whole glass is going to fall out. I mean, it could, but they consider failure whenever the glass comes in contact with aluminum. When that happens, they go, no, that's failure. probably is not going to break. But again, the code takes a somewhat more conservative approach and saying, let's just not allow any contact between the glass and the mullion tongues or the mullion, whatever part of metal is close to the edge of the glass.
I will say that, in the testing, the lateral shake testing that they do, you can actually get a lot more out of a system than you can by any calculations or anything like that, because there's a lot more redundancies built into the system, and it can actually contact glass, not break the glass. I've seen tests where it's just the glass is almost coming out of the thing, and it's a miracle that it's actually staying together. And you see it at the end of the test, it's all back to kind of square. It's like, okay, it passed.
Yeah.
But you can't get there with the calculations and so it's always better to have those tests to be able to try to validate.
And something that's been in our to-do list for quite some time, but we did want to reach out to ASE 7 and the committee, because one of the things that the equations don't take into account is the glass always sits in those two setting blocks. The equations, our understanding of how the equations are written in the code, they kind of assume that the glass is kind of like just floating there. It doesn't take into account there's two setting blocks there holding the glass.
Yeah, they don't mention that. They don't take into account. And that does make a difference because it's like a pivot.
Yeah.
Yes, yeah.
It does.
The jams. I'm assuming that that's sort of like a receptor, and I've seen that every once in a while, where they've ran, like storefront receptors, and they've got it over the head, and then they have it at the jam as well. So I would say that it's an unusual situation. I've never really, seen it used much, but in high seismicity types of environments where you need to have some extra space there for that racking, that could be a great possibility where you have to have something like that. Otherwise, I don't see a need for any type of compensating.
And actually, that
jam.
could have an impact to the ability of the head receptor to accommodate movement. Remember, we had a project, I think it was Chicago some years ago, in which, because you have the compensating channel on the side, mitered at 45-degree angle, so it can be installed with the head receptor. And now you're kind of locking that head receptor. It can't move because you have the comp channel on the side and it's acting like a post. Yeah. I mean,
So
most
you
of
gotta
the
be
movement,
careful with limiting.
most of the movement is going to be closer to the midspan of the opening anyways. But there might be a case that compensating channel compromises the ability of the head receptor too.
Yeah.
So, but yeah, I don't think we've come across so many
Not too many
compensating
times, no.
channels. Yeah.
Yeah.
And what's for Michelle? What is the misunderstanding
Of crush panels? Okay. Yeah. Can you speak to that?
What's
So-
crush panel?
So a crush panel is where, usually at the edge of a building, where you have to be able to allow for probably, some very rigid systems to be able to laterally move over into those crush panel areas. And usually it's thin, type metal, and it'll allow for that to move into that area, crush the panel versus crush the glass.
I see. Yeah.
And so it saves the glass. The panel crumples. It can always be replaced, but glass is not falling on people. And so that's usually the purpose of those types of applications.
Yeah.
next, from those who are in the blood list. Good road with that. It shows system tests DLI are smaller than the projected DLI. All our formulas accept. Will this apply to the two-sided SSG in order to avoid doing project-specific testing? Filing one of the words.
Boy, that's a run on. Go ahead. Javier.
threw me under the bus here, huh? Yeah, I mean, it's the vertical edges would be SSG, I'm assuming. The bottom and top would be captured. I still feel that the equations, we can modify some equations to see, okay, there is this much gap between this glass and this other piece of glass. And we can take the C1 and C2 values based on that side. Because I'm thinking while I'm answering, the SSG, after a seismic event, the building owner is going to expect some level of damage. They don't want the building to collapse or the curtain wall to fall, but they will expect that there's going to be some seals and maintenance that's going to have to happen. So my approach with that would be maybe modifying the delta fallout equation so that instead of the clearance between metal and glass, we take this joint, half of the joint, basically, to allow each piece to travel that much. Basically, take your glass, replace the mullion tongue by the glass, and say, let's not allow the glasses to bump into each other. So I guess, yes, we could somewhat find a creative way to modify those equations. And I mean, this is proof that the seismic requirements in a very young industry like glazing and curtain wall are catching up to some of these. So I'm sure that in our lifetimes, we will see more advancements on the code that allow for more engineering, like analysis and rational analysis for those. Most SSG systems out there on the largest manufacturers have test values for those. And they try to test big DLOs. In-house, like I showed on that flow chart, if a project DLO is larger than what was been tested, we have some rational methods to try to extrapolate that result within certain limits, of course.
Any reductions?
No, gotchas.
Gotchas.
Yeah.
With glass guardrail.
Yeah.
Yeah.
Anchoring into concrete would be one.
Yeah.
There is the omega, which is called overstrength factor, which you have when you have a guardrail system that is the base shoe is anchored directly to the concrete slab. We calculate our wind load pressures, our seismic lateral load on that guardrail. And you think about it, it's a cantilever, 42-inch cantilever piece that when the building moves, that thing's going to want to do this. The interior wind load pressures are minimal, or 5 psi. So we take into account the 50-pound per linear load from pedestrians, the 200-pound impact load from somebody falling. But many times in the West Coast, we see that the seismic requirement on those bolts, it's what governs. Because that omega factor, that overstrength factor I mentioned, the code requires us to multiply that load times 2, because they consider cement a brittle type of failure. If that concrete spalls or the bolt disengage from the base shoe, it could be a very sudden type of failure. So that's why they include that omega factor into those connections. So when you see a guardrail, Nick, you know about this, when you see a guardrail that's 1 inch from the edge of the concrete slab, stop, call us, get us involved, because that is definitely going to be a challenge.
I will add to that and say that one of the biggest gotchas is don't believe the architect and what he has in the drawing. Don't believe that, because, yeah. And, I'll add a little bit there as well. You really have to watch out for, it's most often, it requires laminated glass. It just is. It's going to be laminated glass now. And so architects are still, they're getting up to speed in a lot of areas. So watch what's spelled out in the architectural drawings whenever you're doing takeoffs and stuff like that. Mm-hmm. And don't necessarily believe what's in there, because it's not right. And then on top of that, I'll say that whenever you're in rooftop situations, here's a gotcha. Whenever you're in rooftop areas, I've seen cases in the past where they want to have the handrail mounted kind of flush with the floor system that is raised floor system, so that it looks like it's, brainless and it's just glass, coming up through the floor system. You have to watch out for that, because if you go all the way down, there's additional load that you have to take into account. And so the forces are larger whenever you're going a longer distance down to anchor, and you really have to account for that in the thickness of the glass. That's one gotcha. Another gotcha on the rooftop system is that whenever you're looking at the waterproofing membrane, you cannot have the waterproofing membrane in between that and the channel of the glass. I've seen some architects call that out and want to say, no, you cannot break the waterproofing membrane. Well, the doggone thing should have been on a raised area to begin with, and that waterproofing membrane brought up and out and then anchored to the top of a kind of a system that's raised. But don't do that, because that will really mess up your glass handrail, and somebody's going to come along and say, uh-uh, this isn't good, because it creates that cushion in there and it won't work.
Always, I would recommend to start off assuming that a 3/4-inch laminate would be required. 1/2-inch glass,
Especially exterior.
yeah, seldom would 1/2-inch glass. I've seen it very few times that it works, especially for point supported glass too. When you have spider fittings that are holding the glass, or like offsets that are holding the glass, a 9/16 laminate or 1/2-inch laminate glass will 98% of the time not be
Stress
sufficient.
concentrations around the
Yeah.
holes. Yeah.
End lights
Hey,
too,
Stuart?
the top cap. Some systems have been tested and they say, okay, if your top cap can't anchor to a substrate above, you have to limit the end light, like, because if the glass breaks, you don't want the top caps are quite light and not too strong. So you don't want the glass to break and have that top cap like fail.
Not able to support the load that needs to still remain on it
Yeah.
after the failure of that end piece of glass.
Yeah.
So usually whenever you have the returns of, outdoor glass rail, usually they're returning into, curtain wall or something, glass, and you can't connect it. It's really preferable to have a connection to the wall at that in return. That way you can run longer pieces of glass, but that in return is confined to whatever that top rail can actually do in terms of structural support, because you got to count like the glass is broken, and that's got to be able to take the full load of somebody impacting it without giving way. Yeah, those are some
Stuart,
gotchas.
if you have like an just like I had a job at Children's Hospital, it's shaped garden protecting from falling to the pool to the first floor. So how would you anchor that top cap? Because just
It continues, right?
It's continuous. Well, that's actually
It anchors
we
itself.
can, you can model that. Yeah, and you can actually model that and show, that it's all fully connected. As long as there's welded systems along the way or anchored systems, and it's one continuous member, you can actually model that and show that it's capable of
Is it
being able
curved
to.
glass? Yeah. So
Yeah.
that's actually a pretty strong
Oh, that's
setup.
that's
Yeah.
nice.
We wouldn't require any posts, probably, Yeah, it kind of anchors itself. It's a one rigid.
because right now there's ankle line, quarter-inch ankle line down supposed to attach. But we send out, I don't know if you heard of GPRS, they came out, we took plot points of everything, the data camera, and we identified that the angle bar is not at a true radius. So at some point I'm going to be off center from the angle bar. Other points I'll be right against concrete, kind of like floating all over the place. So this engineer recommended we extend it. But we can't do that now because some areas it's really tight line. Other areas it's still got a 2-inch gap. So now we're looking at attached to the concrete.
Yeah.
Side me. That's it. And if that's something you I'm up against.
Well, yeah, side mounts are, we just did it recently, and it's an option. Concrete edge systems would be an option. Some of the slabs are only, especially if you have corrugated metal underneath, like concrete over metal decking. Some of those places are like 3 inches deep.
Yeah.
And sometimes they use lightweight concrete for seismic reasons. So lightweight concrete and a basal anchorage, it doesn't offer that much capacity. For that, and the spacing and the embedment and edge distance is the number one limiting factor in concrete connection. Yeah, you don't want to get too close to the edge.
Hey, Stuart.
It's up to us so our sealed package will be conclusive for like all the requirements. So
Yeah.
we haven't seen
I
our approach
haven't seen-
flagged.
Yeah, I haven't seen a lot of that. Well, I mean, could, but yeah, haven't seen a lot of that.
Your engineering, your calculations, are these guys calculating like PBV on effects or SGB?
Depends if it's exterior or interior.
Pretty much. Yeah. Pretty much always on exterior.
Yeah.
And
We did PBV because I know it's a little more expensive.
Mm-hmm.
Yeah, for guardrail.
Yeah, it could work. I've done, and I think one of the problems with the SGP was sourcing it too. This is a crazy weather story that Houston got this like incredibly cold snap couple like 5 years ago or 4 years ago, and that derailed the entire SGP like supply for the country.
froze
And
all their vats.
yeah, so one of the materials that was used in SGP got like damaged, and our clients were just like, we can't get SGP. Like you can't source it. But no, for interiors, I think PVB would be if it calcs out, we see no problem.
It is weaker. It's obviously weaker, and yeah.
I don't think so. For
What's that?
if there's for glass breakage, it doesn't need to be SGP. PVB can also could still hold the pieces of glass together.
It can, yeah, it can still hold the pieces of glass together and keep it from falling on, people down below. That's what the real issue is. The issue is whether it's strong enough to be able to act with one ply broke in the case that it doesn't have a railing across the top. And in those cases, whenever it doesn't have some type of rail across the top or something connecting, then PVB is not going to make it.
Yeah, because you have to take if the architect is really saying no top cap, we want just the glass. We do need to run a chapter 24, I think, in the IBC requires us to run one ply broken of the laminate.
Yeah. Yeah. It is pretty much required anymore anyway. Yeah. Yep.
Yes.
It's just a slide on, isn't it? It's just Hey, Stuart, can you hear me? I want to be quiet. He's from our team, so can you hear me? Ultimately, you get into situations on outside where you have wind screens, not just a handrail system. They become wind screens. Very difficult to do with wind loads outside. And so there is a requirement that we look at it. If it's a certain amount of distance away from the building, we have to look at it as if it receives parapet loads. Does anybody know the difference in, parapet loads and regular wall loads? Parapets, man, it just huge amounts of loads, suction loads on the outside, and then a lot of positive pressure on the inside of it. And so those parapets have to be designed to resist a heck of a lot of wind load. And so I think it's, more than 8-10 feet or something like that.
I think there was an article wrote that 6 times the height of the guardrail. So 6 times 42 inches.
Okay. Anyway, there's a formula that, at a certain amount of distance away from the building, we have to design it as a parapet. And that becomes extreme, with those types of wind loads. In addition to that, the taller that you push something up and you're trying to resist wind loads and all the other loads that are on it, it becomes extreme, down at the bottom. The thickness of the glass grows, and then the anchorage of whatever system that you're trying to, it's probably a post system by that time that you have to put post in, and the anchorage of that post structurally becomes a nightmare, trying to get that into like steel frame members and concrete members. You really have to look at those details closely. Yeah. Good questions. Are we needing to go? Okay. Right. Yeah.
Reassuring on that and guardrails. So that's now I'm running down how to get back.
Yeah.
Yeah.
That vehicle is already well away.
Yeah.
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 Retrofits are especially challenging because of the availability of construction documents. And we sometimes have to make some assumptions. And there are some concrete mold companies like Hilti is really good about this, that they would send out people to the field and do some field testings for capacity, especially if we're anchoring into like stone. What stone? Like we don't have any values for stone. But yeah, retrofits could be a little bit challenging for the availability of documents for us to use on the calculations. Like Stuart said, short little balconies that are only like 4 or 5 foot from the face of the buildings, we're okay making a call that it's just the regular zone 4 or zone 5 wall pressure.
Regular, wall zone pressure.
Wall zone pressure. But if the balconies are a little bit deeper, they allow that, like Stuart was saying, that positive pressure to build up and act in conjunction with the negative. And you can go from, like in Florida right now, we're working on a project that went from 68 PSF wind load pressures. We realized that the balconies were quite a bit deeper, jumped up to 123 wind load pressures. Not even a 1-inch piece of glass can take that much load, So the depth and the geometry of the balconies do play a factor on how we approach. And that's also part of that's kind of an engineering judgment that we have to hang our hat on some research or some paper. It's not like a prescription by code, as many things in this industry, but we have to make some judgments based on just engineering concepts, knowledges. There are some prescriptive methods in the codes, but there's a lot of just experience and judgments that we have to make.
Good questions.
Like with like early on, like pricing. There's a lot of people we're looking at a job, and we work with the engineers, or we're saying, hey, look, we have a issue one good with or we're trying to figure out the pigments of glass for a certain height, which we for example.
Yeah.
Let's just say we want to make them a something, but hey, we're going to use 3/4 maybe with a heavy base shoe, maybe a custom base shoe. But we don't want to take that liability and just get all the job like that. And when we turn it over to you guys, we got some, no way, it needs to be 1-in-8 Miami, and now we can't get the extra money. And we sent that stuff to you guys early on. Can you guys say, hey, Kenny, Drew, in order for you guys to do this, you need, triple Miami or whatever. And that way we can make that assumption in the proposal, because if we side the way we're making stuff assumptions, then we may some money in the project.
We can, but it takes a small amount of engineering time to be able to do that. And so it's, but that may be, like a couple hours, of us getting into our software program and plugging that in and finding that out for you. So it's not like it's going to be like the whole project.
Yeah.
So
it's part of the
it might be worth it to be able to have an accurate, because that's a huge difference in glass that, you could save a lot of money, by
some of it.
Yeah. I mean, putting together a calc package does take some admin time to like just bring everything together. But a quick check, like Stuart said, it's part of the preliminary services that we offer. And it's a marginal cost compared to the full-blown engineering for that system, because we're not looking at anchors. We're looking at the basic like applications of that glass and running a quick analysis with our finite element model and give you a quick answer like, hey, yeah, you're in the ballpark. You can probably make it work, or no, wait, just go with 3/4 inch, So that's definitely, and like Stuart said before, that helps solve so much problems down the road.
You get into variability of wind loads too, design loads with buildings based on height and where it's at and all the other stuff that, vary quite a bit. But ultimately, I understand what you're saying, but we also take on a liability every time we issue any type of an opinion. It's a liability to us as well. And so,
engineers can be wrong sometimes, but we try really hard not to. But it's our words carry some weight that not that great all the time to have that in our shoulders.
Yeah,
we try to be accurate.
Yeah. Enjoy. Thank you all. Thank you for your time.
Thank you for
Yeah.
coming. Yeah.
Yeah, thanks.
Thank you.
Administrator,
Thank you.
about you.
Thank you for your help too. That's